All right, so 10.4 is about arc measures. We talked about, I don't think that's the right title. I forgot to update that. It's not about arc measures. It's inscribed angles. I'm sorry. Inscribed angles. Yeah. I just looked something right. This is on inscribed angles. I just forgot to update the title. And these are, we talked about central angles, which are angles that have the vertex at the center. Today we're going to talk about inscribed angles. And an inscribed angle is an angle whose vertex now is on the circle. So previously we talked about central angles. They were little like pieces of pizza, right? Their vertex is at the center. Now we're going to talk about inscribed angles. So this is not inscribed, this is the central. So inscribed angles are angles whose vertex is on the center and whose sides are chords. I'll draw a picture of that in a second. Whose sides are chords. Inscribed, what does the scribe do? Write stuff down. In means inside. So inscribed literally means inside the circle. So if you draw a circle, your inscribed angle, notice how the vertex now is on the circle. See how the vertex has moved? It's no longer in the center. This is your inscribed angle. Notice how the two edges of the angle, the rays, or the segments in this case, are the chords. You see how they form chords? The intercepted arc, then, is the arc between the chords of the inscribed angle. So the arc is, remember, like the crust of the pizza, so to speak. So the part between the chords would be right here. Everybody see that? Notice how it's highlighted, bounded by the two chords. This is the intercepted arc. This may work for some of you. I always, when I think of these, I always think of them as someone shining a flashlight in a circular room. You got, when you shine a flashlight and it gets bigger. I always think these kind of look like them, and then the intercepted arc is where the light would hit the side of the wall. Pizza's fine too, but pizza you don't cut like that. Pizza's great for the central angle.
Oh, no, I'm just thinking of angles. Like this part is inscribed angle, and you got the different parts of the crust.
Sure. What? Jumbo slice, yeah. Alright, so whatever you want to help you out is fine with me, okay? So if we go to this GEO plate while it loads, okay. So the big angle is called the inscribed angle, and then the part that it hits, the arc, is called the intercepted arc. It's the two words right above it. Definitely. That was called the central angle. The next one is called the inscribed angle. Okay.
That means that it's always up in that possible side. Isn't it not the same for like the chords always equal to the side?
Not necessarily. I can draw an example in a second.
Okay.
So if we look at the difference between central and inscribed, central, remember the vertex is at the center. inscribed, the vertex is on the edge. Notice the blue line at the bottom? What's that called? Intercepted arc, okay? So as I move the point B around, notice that my intercepted arc is going to stay the same. If my intercepted arc stays the same, notice that my angle also stays the same. Does this make sense? So the arc stays the same, the angle stays the same. Now if I move point C, however, it's going to change both of them. What do you notice about the relationship between the central angle and the inscribed angle? They both get smaller? Can we be more specific? Is it like half? It's always half. Everybody see how it's always half? One cool thing that I want to do on this page, do you agree with me that it's always half? It's hard, there's some rounding error, but you notice that whenever it's an even number for the central angle, it's exactly half. One cool item that I want to bring up that we're going to talk about in a second, notice that when I go to 180, what kind of angle is the other one? 90. If I ever draw a diameter, this is a diameter straight across the circle, and I complete the triangle on one half of it, notice that the triangle, wherever I move it, is always going to be a right triangle. So if you ever want to construct a perfect right triangle, draw a circle, draw the diameter, and then complete the triangle. Now the problem is you have to draw a perfect circle too. So that kind of stuff. All right? So our conclusion, we could say that the central angle is how much bigger? Double. 2 times or double? So 2 times as big as its matching inscribed angle. Two times as big as its matching inscribed angle. Okay? Does that make sense? Do you believe that from the pictures? Don't worry about that. We just covered it. Some quick practice. Quick practice. Find the measure of the missing arc. So this one is hard to see, but I'm asking for the measure of TV. Measure of TV. So if we're looking, we measure angle TV by the central angle, right? So my central angle would be right here. Everybody agree with that central angle? We measure the arc by the central angle. Which one is bigger, the inscribed or the central? So it's how much bigger? 2 times as big. So if I'm going to find TV, I need to take 38 and multiply by 2. So what am I going to get? 76 degrees. So TV is 76 degrees. Whenever you go from an inscribed angle to the intercepted arc, you need to multiply by 2. So inscribed angle. You may want to write this down. Inscribed angle to intercepted arc. You need to do times 2. If I go the other way, then I would need to do what? Yeah, divide by 2. I'll do that in a different color. If I go the other direction, I need to divide by 2. Pardon? The central angle would, so I tried to draw that as close to the middle as I could. Does it have to be in the middle of that angle? No. For example, let me draw an even bigger one. Here's the central angle. All they need to share is the same intercepted arc, right? So the endpoints need to be here, but it could be, for example, way over there. As long as the vertex is on the edge of the circle. We're going to get to that in 1 second. Yep. This right here. If we're going from the inscribed angle, 38, to the arc, we need to multiply by 2. If we're going the other way, from the arc to the inscribed angle, we need to divide by 2. We're going to practice it on this page, okay? Take a look at the next one down in the bottom. Slightly harder. Thoughts? What should we do? I want to find arc SQ. Naomi? Should you write the diameter? Where? From where to where? So, I like your idea, but I'm not sure that that center is right in between them. So it doesn't say that these are on the diameter. So if you take a look, I don't know, it looks okay, but it looks a little bit off to me. So you can't assume that that's going to be diameter. Arden? So times 95 by 2, because we're going from the inscribed angle to the intercepted arc. Does everybody see that? So what is arc RQ going to be then? This is going to be 190 degrees. But we're not quite finished. What do they want? How do we find SQ then? How many degrees are there in a whole circle? Yeah, we learned that before break, so I realized it takes a while. But there's 360 degrees total, correct? If I have these two arcs, can I find the missing piece?
Yeah.
What is that going to be then? What is it? So this will be 95 degrees for arc SQ. Intercepted arc, or inscribed angle, times 2 to get the arc. So 95 times 2 got me the arc. Yes, ma'am? 95, because there's 360 degrees total in the circle all the way around. So if I know this is 75, and I know this is 190, well, the only piece left is what I wanted, right? So I can figure out what that is using addition and subtraction. The next one, any thoughts on how to find that arc? Kevin? Okay, so Kevin said that's a triangle. Triangles all add up to how many degrees? So if we have B and C, can we find B? What would B be? 60 what? Yep. So 61 degrees, then what? Yeah, multiply by 2. It's kind of hard to see, but if you look at your angle right here, here's your intercepted arc again. So if I'm moving from the angle to the arc, I need to multiply by 2. So arc BC would be 122 degrees. Yes, ma'am? Why isn't any other arc an arc? I'm confused by your question.
Why don't we find like the other arc? Are you trying to do that? Because for B, are we trying to find the one across the way? Or are we trying to find the one?
You're saying why are we not finding this arc here?
Yeah, what's the other?
Because the question mark's over here.
So where are the
You could find the other ones if you wanted to. Because remember, inscribed arc times 2 gives me the, inscribed angle times 2 gives me the arc. Here's my inscribed angle. Notice how it's on the circle. 61 times 2 gives me the arc, which is 122. If we go the other direction, this says if I give you the arc, If I gave you 122 evidence, and I wanted to find the angle, you would have to go the opposite direction. So you do 122 divided by 2 to get 61. Yes, ma'am? Yeah, so I might have just asked, is there another way to do this? And there absolutely is. If you found, you could do 49 to arc BC right here. You could do 70 to arc BB over here. And then you have the two pieces. Can you find the third piece? Sure. And it will give you the same answer. Okay? Don't need to write this down. Just take a look at it. Notice, first off, AEB. The arc here is 60. If I'm going from the arc, thank you for shouting out, to the angle, what do I need to do? Multiply or divide? So 60 divided by 2 will give me, Kevin, 30 degrees. What about the next one? Is it different? So I get 30. What about the next one? 30. Okay? So what you can conclude from this picture, what you can conclude is right there. If two inscribed angles intercept the same arc, so let me flip back, I'll go back in a second. Notice how they all intercept the same exact arc? If angles intercept the same arc, whoops, then the angles must be congruent. All those are 30 degrees, right? If two inscribed angles intercept the same arc, then the angles are congruent. So if I draw a quick picture, circle. That was a really good one. Let's say my arc is here in blue. I'm going to pick two different inscribed angles. It doesn't matter where I draw them, as long as their edge is on the circle, their vertex is on the circle. I'll draw one that's really funky looking, right down here. What we can say then is that angle 1 has to be congruent to angle 2, because they're shining their flashlight at the same arc, okay? But I like the highlighters. Nice. I did that when I was in high school. So you're well on your way to being a nerdy math teacher. Keep it up.
Ew.
Oh, thanks, guys.
No thanks.
It's the first day back and you're already insulting me.
No, not like that.
Uh-huh. Alright, the next thing we got to talk about is the inscribed polygons, the last thing for today. Inscribed polygons. Inscribed, what does inscribed mean again?
Inside.
To draw inside, yeah. So inscribed polygons are polygons that are where? Yeah, they're inside of circles. They can be any number of sides. They could be a triangle, they could be a square, they could be a quadrilateral, they could be a pentagon, they could be a 20gon, okay? So all you need to do is draw a circle. How many sides do you want? 20? That's going to be hard to draw.
4.
4.
Right.
So 1,
20.
2, 3, 4. Okay, it looks kind of like a trapezoid. What's that called if the sides are the same? Isosceles trapezoid. Alright, so we don't know, but it looks like that.
No.
So an inscribed polygon means in the middle. The circle, what's anybody Latin scholar in here?
Erica.
Oh no.
Hey.
Erica?
No.
Yeah. You may not know it yet. Do you know the Latin word for around? Anybody else? Circum. What does it mean? Who was the first guy to sail around the world? No, Columbus on America. Magellan. So we circumnavigated, right? So this is called a circumcircle. Sorry, not circumcircle. It's called circumscribed. My bad. That is circumcised. But Arden comes from the Latin. Circum still means around. Alright? Circumscribed means to draw around. Right? To write around. The next thing we need to do is for an inscribed quadrilateral. How many sides? 4. The opposite angles are supplementary. What does supplementary mean? Adds up to 180. Oh, I'm getting good. Alright? Draw a quadrilateral. It can be any shape. Sorry. Draw a quadrilateral. It can be any shape. Label it 1, 2, 3, and 4. Ms. Tercius?
Is it true like a perfect circle out of a square? Yeah.
I don't know what you mean.
Like you draw a square and you draw a circle inside and then you break the outside of the square. I don't know. Yeah.
Well, sure, but you have to have a perfect square to begin with. The opposite angle, so we can say that angle 1 plus, what's the opposite to angle 1? 3. Angle 3 is equal to how many degrees? 80. And we can also do it for the other pair. So angle 2 plus angle 4 is equal to 180 degrees. Yes, ma'am? One word. One word. So why does this work? I'm going to show a quick, if you don't get this, don't worry about it, but I want to show the curious. Look at angle 1. Notice it's inscribed arc, okay? It touches all of this. Everybody see angle 1? Look at the opposite one, angle 3. It touches the other half of it, right? Or roughly half. So between 1 and 3, don't they intersect the entire circle? Yeah. And then if we want to find the angle, we go from the arc and we divide by 2. So 360 divided by 2 gives me 180. Okay? Yes, ma'am?
Oh, no.
Go back. Oh, sorry. Oh, no. Lost it. What's up? In my picture, they were directly across from each other. You could draw any quadrilateral, though, so they don't have to be. For example, oh, sorry. So in this case, you can see they're not evenly spread out. I'm a little confused by the question, but I'll have to answer it in a second. Let's move on to some practice problems. Any thoughts on how to do this one? I want you to find the measure of NLM. So eventually, I want to know that measure. Any thoughts here? Yeah. Okay. We could, but you want to do 7x minus 10 divided by 2? So that's part of it. Sarah said, eventually we want to take this arc and divide it by 2 to find that angle, but we need to have a numeric value. The whole thing is 360.
So then, can you just add the upside for those two? Breaking it with 7x squared 10. minus 10 plus 7x minus 10 equals 180.
Perfect.
Yeah, conference.
13x minus 10 plus 7x minus 10 equals 180. Notice that this is a diameter. Diameter splits it into two, what do we call half circles? Semicircles. How many degrees is a semicircle?
180.
So notice that the arc for a semicircle is going to be 180. So the small piece plus the bigger piece is equal to 180. Does that make sense?
Yeah.
If we solve this, we get 20x minus 20 equals 180. So we get 20x equals 200. So therefore x equals 10. What should I do now? Sorry, keep rolling.
Oh, you plug in x to 7x minus 10.
Plug it in down here. So we get, go ahead.
Oh, you 70 minus 10.
It is. So this is 60 degrees. Are we done?
No.
Divided by 2, because we need to find the angle, not the arc. So we divide by 2, 30 degrees. Okay? Very good. These problems will involve many steps, okay? They'll involve many steps. And you may just have to, if you're ever confused, try and find out as much as you can, because it may come back and help you later. Right? So here, like, it didn't really ask for x, but you might as well figure it out. Okay? Odds are, if they give you an x, you're probably going to have to figure it out at some point anyway. Right? Last one. Somebody? How do we do this one? Where? So you said they're equal? Do they look equal? This one looks acute. That looks obtuse, right? Harvey?
41x minus 2 equals 3x. I mean, 38x plus 5 equals 1x.
You just gave me two equal signs.
Okay. Add angle G and angle A.
Okay. Add them together?
Yes.
Correct. And that's because on the 2 slides ago I told you that opposite angles add up to how many degrees?
180.
180. And then we'll solve this real quick. This is 49x. Did I write this down right? Oh, I'm sorry. Thank you. 59x plus 3 equals 180. So 59x equals 177. How many times does that go in? Divide both sides by 59. X equals 3. A hint for you guys for big number division. We know that it's going to be 59 times something, right? So look at only the 9 and look at only the 7. 9 times 1 is, that's not going to work. 9 times 2, 18. So we need an 8 in that spot. That wouldn't work. 9 times 3, 27. Oh, there's your 7. Okay, so then you can finish it to make sure, but you only really need to look at the last 2 numbers. Okay, yep, mental math. Your homework for tonight? It's right here. Oh, he froze. Let's try it again. Hang on. He froze. All right, so your homework for tonight is right there. We're going to finish the chapter tomorrow. We're going to then review on Friday, maybe start the next thing even. And then your test is going to be on Monday. So test on Monday. We'll probably have a quiz on, well, we'll definitely have a quiz, 10.4 through 10.5 Friday. No, because you won't have the stuff yet. Because you're learning 10.5 on Wednesday. Oh, perhaps. Talk to me actually later. So we have that on Friday, and then the test is going to be on Monday. We are skipping a few sections, okay? We are skipping a few sections. So the test is Monday, and that's going to cover 10.1 through 10.5. Okay. Excuse me? Come back? Probably not. It's 17. Hang on, let me just stop the recording and I'll put it back.